Vector applications. For the first example, it says find the component of form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle of 30 degrees below the horizontal shown in the picture. So if this is 30 degrees below the horizontal and they're adding the 180 from that, so they're saying this angle is 210 degrees. So we've talked about how to find the component form given the magnitude and angle. So remember we said that, so this in this case the angle is 210 degrees and the speed, which is equal to the magnitude, is equal to 100 miles per hour. So remember that the formula is the magnitude, which is 100, times the cosine of the angle, and then the magnitude times the sine of the angle. So then we just need to make sure our mode is in degree mode in our calculator. And we can just type this in. If it's something on your unit circle, we can use your unit circle. So we actually don't need our calculator for this. We can just do this without the calculator. So we have 100. The cosine of 210 degrees is negative root 3 over 2. And then we have for the vertical component, 100 times the sine of 210 is negative 1/2. So then for this one, 100 times negative root 3 over 2 gives me negative 50 root 3. And then this would give me negative 50. So this would be the component form of the vector that represents this velocity at the specific direction that we have. So recall that the resultant force is the sum of all the forces acting on an object. So for this next problem, it says an object at the origin is acted upon by two forces. A 150-pound force makes a 20-degree angle with the positive x-axis as shown in the picture. So this would be a 100-pound force. And then, oh, whoops, sorry, that's the 150 for this one. So 150. And then the other force of 100 pounds makes a 70-degree angle with the positive x-axis as shown below. So this one was the 100. We want to find the direction and magnitude of the resultant force. So here you can see that if we use the parallelogram law, then the resultant force is going to be from here to this point. So in order to find that, we want to figure out first what the component form is given the magnitude and the angle for the first part that we have. So we have 150 times the cosine of 20 degrees, and then 150 times the sine of 20 degrees, and that's for OP. And then for the vector OQ, that's going to be equal to the magnitude, which is 100 times the cosine of 70 degrees, and then the magnitude times the sine of 70 degrees. So once we get our component form, remember to find the resultant force, then we're adding the horizontal and vertical components together. So we're going to add these together to find the resultant. So this is going to give us OP plus OQ. And so we can just type this in the calculator. So 150 times the cosine of 20 plus 100 times the cosine of 70 for the horizontal component. So this would be 175.1, I'm around using 4 decimal places, so 1559. And then if we do the same thing except for change the cosines to sines instead, oops, then we end up with 145.272, and then that would be 3. So now that we have our horizontal and vertical component, you kind of see that makes sense because your x value is positive and y value is positive. So that's saying that then for this resultant force, the distance from here to here, that's not a very good straight line. So the distance from here to here is 175.1559. And then this distance, that is the vertical distance, is the 145.2723. And so if we want to find the direction and the magnitude of the resultant force, then of course that means we are going to have to use the Pythagorean theorem to find the magnitude. So the magnitude of the resultant, which we'll call OR, is equal to the square root of 175.1559 squared plus 145.2723 squared. And then again, that's because this makes a right triangle here. So we're just using the Pythagorean theorem. So the square root of 175.1559 squared, and if you had a negative, you'd want to make sure to put that in parentheses, but there's no negative here, so it doesn't matter. 145.2723 squared, and we get the magnitude of OR is equal to 227.560 and then 2 pounds. Again, that's the magnitude. And then for the direction, remember, because we have the horizontal and vertical component, that's the opposite and the adjacent. So we're going to use the tangent. So the tangent of theta is equal to 145.2723 divided by 175.1559 because it's opposite over adjacent. So in order to figure out the angle, we have to use the inverse tangent. So second tan, we get 145.277 or 22723 divided by 175.1559, and that gives us theta is equal to 39.67, so we'll say 39.7 degrees. And of course, you always want to make sure you're using the correct quadrant. So your resultant component form is in quadrant 1. So that makes sense that this is in quadrant 1, but remember, if it was in quadrants 2 or 3, you'd want to add 180 degrees to that answer. Okay, so the next problem, using vectors in navigation. So remember, we've talked about navigation before. So navigation angle measurements are clockwise from due north. So remember, this would be 0 degrees at north, 90 degrees at east, 180 degrees at south, and 270 at west. So a heading is clockwise again, due north, from due north. The airspeed is just the plane speed, speedometer, just the plane alone. The ground speed is the result of the air and wind vectors, which is your direction, also clockwise from north. The course is the result of the air and wind vectors. The direction is, again, also clockwise from due north. And we're not going to talk about the drift angle, but it's an angle from heading to course, not from due north. But again, we're not going to worry about the drift angle for right now, so we're just going to look at the rest. So this first example, or this example here, says an airplane is flying in the direction of 75 degrees with an airspeed of 210 miles per hour. So what does this tell us? This tells us that the airspeed is the magnitude of the plane. And it says the direction is 75 degrees. So we are talking about, again, from north. So north, east, south, west. Remember, this is 0, 90, 180, to 70 degrees. And so 75 degrees from north would be about somewhere over here. This would be 75 degrees. So we want to figure out the component form for this. So we need to figure out what the horizontal component is and the vertical component. So that means in order to do so, we first need to find the standard angle, because remember, your calculator uses standard angles and not navigation. So that's why it's always important to convert. So we're going to first convert to a standard angle. I guess I should have read the rest of the problem too. So a wind of 50 miles per hour is blowing from the direction 150. Find the course and ground speed of the plane. Navigation bearings are measured in degrees from clockwise due north. So for this one, the standard angle, we've talked about how to convert this. So 90 minus 75 gives us 15 degrees. Now that we have that, we can go ahead and figure out our horizontal and vertical components. Again, knowing that the magnitude of the plane is 210 miles per hour. So remember, we said for the component form, so this is for the plane. So the component form would be equal to the magnitude times the cosine of the angle, and then the magnitude times the sine of the angle. Okay, we're going to leave that like that for now. And then it says a wind of 50 miles per hour is blowing from the direction of 150 degrees. You have to be careful here because it says it's blowing from the direction. So if we're blowing from and not in the direction, that means we're going the opposite direction. So it's just something that you're going to have to remember. So this is the opposite direction. So first we have to figure out 150 degrees in navigation. So north, east, south, west, this is 0 degrees, 90 degrees, 180 degrees, 270. And so we know that 150 degrees would be down here. So that from here to here is 150 degrees. But because it says it's blowing from the direction of 150 degrees, that means we're actually going 180 degrees the opposite direction. So we need to figure out from here to here what that standard angle measure is going to be, because that is going to be what we're going to use to find our component form. So a couple different things you can do. So you know that all the way from clockwise due north, if we go all the way around, that makes 180. So for this one, we would have then 180 degrees minus 150 degrees, which is equal to 30 degrees. So that tells us this angle measurement down here is 30 degrees. So if that's 30, then we know these are vertical angles. So this measurement also is going to be 30 degrees. So we know then we can take 90 plus 30 degrees, because remember the first quadrant from here to here is 90 degrees. So the standard angle would be then 90 degrees plus 30 degrees, which of course is equal to 120 degrees. Or like I said before, you could use that trick that we learned to change from bearings to standard angle. So if you did 450 degrees minus 100 and no, I'd have to be not the 150 because that's from the wrong direction. So if we did instead from north all the way to here, so that would be 360 minus 30, so that's 330 degrees. So you need to use that measurement, not the 150, sorry. So this would be minus 330 degrees, which would then give us 120 degrees. Again, you can use whatever, however you want to do that, whatever works for you is fine. So now that I know that that measurement in standard angle is 120 degrees, we can find the component form for the wind. So it's going to be the magnitude, which is 50 miles per hour, so 50 times the cosine of 120 degrees, and then the magnitude, which is 50 times the sine of 120 degrees. And then the next part, we want to find the course and the ground speed. So the course is going to be the direction of which you're going, and then the ground speed is going to be the magnitude. So we want to find the course, which is the direction, and then we also want to find the ground speed, which is the magnitude. So that means we need to find the resultant component form first. So for the resultant force, we take the plane plus the wind and add those components together. So I know that 120 degrees is on our unit circle, but 15 degrees is not. So we're just going to go ahead and do this in our calculator. So 210 times the cosine of 15 plus 50 times the cosine of 120, which gives us 177.8444. And then the vertical component, we do the same thing, except for instead of using cosine, we use sine. That gives us 97.6533. So this is in quadrant 1. So again, always good to look at what quadrant you're in to make sure that you don't need to change something when you're finding the direction angle. So this means that we are going over 177.8444 for the horizontal component, and the vertical component is 97.6533. So again, we're trying to find then the angle and the magnitude, which is the plane plus the wind. We need to find that magnitude. So to find the magnitude of the plane plus the wind, remember, you're just using the Pythagorean theorem, so it's the square root of 177.8444 squared plus 97.6533 squared. Again, if those were negative, I would make sure to use parentheses. So the square root of 177.8444 squared plus 97.6533 squared gives us the magnitude, or which is again the ground speed, is equal to 202.89 miles per hour. And again, that's because the wind is going this direction, and then we have our plane, which is going this direction. So this would be the head to tail method of finding the resultant. So that gives us this resultant right here, if you wanted to think about like that. But we're still not done, because we still need to find the direction angle, which is the course. And so remember, when we're finding the direction angle, that's really the standard angle that you're finding. So we're going to have to convert this back to navigation. So the tangent of theta is equal to opposite over adjacent, so 97.6533 divided by 177.8444. So tangent inverse 97.6533 divided by 177.8444. And that gives us theta equals 28.7, let's do 28.8 degrees. And this is a standard angle. But of course, the problem's using navigation, so we need to find the navigational angle, which would be from due north going this direction. So in navigation, the course would be equal to 90 minus 28.8 degrees, which gives us 61.2 degrees. So we could write out then that the course of the plane is 61.2 degrees and has a ground speed of 202.89 miles per hour. And that would be it for this problem. So again, the hardest part is converting from navigation to standard angle, finding the component form, and doing that for the plane and the wind, and then finding the resultant, and then changing that back to a navigational. So remember that the ground speed is just a result of the air and the wind vectors, so both of them, and the course was a result of the air and wind vectors, but the course is the direction that we're talking about, and the ground speed was the magnitude. So I'm just going to make a little note. This was the magnitude, and the course was the direction. And that is all for our applications today.